the mini course of Maurício Corrêa. It's about from both residues formula to equivariant localization.
Okay, thank you very much, Ariel. So let us continue. In my last talk, I did this computation for a complex vector bundle decomposable, which is much more simple to compute the chain classes. It's just the product of this xi is the first chain class of every single linear bundle. This is the chain character, which is the sum of this exponential. So this is the most important example, because the big picture we will use this splitting principle. It's enough to know how to compute the chain class for completely decomposable vector bundle, right? So some example. Okay. What is the splitting principle? The splitting principle is it's a way to come everything into a manifold who the vector bundle is splitting, and by using the axioms of chain class we can anyway do this theory and prove the unicity of the chain class. So this FLE is the complete flag bundle of the pullback, and we can take the pullback of E, and the quotient of this vector bundle is a linear bundle. Okay, so we can prove that this is splitting isomorphism. So there is a manifold, a flag manifold, such that the pullback of the vector bundle is split. Okay, so by using Le-Riche theorem, we can prove that this pullback actually injective. This is very important to come back to the base. Okay, so the idea here is to build this flag manifold by iterative projectivizations, step by step, and the Le-Riche gives freeness over the base, so we will get the injectivity of the pullback. Okay.
So is it the cohomology of the total space?
The cohomology of the total space is a module of the cohomology ring of the total space is a module of the ring total space of the base.
And it's free?
Yeah, it's free. Yeah, actually.
And is it the tensor product of the algebras?
Yeah. Right. Thank you. Okay. Let us remember what happened here. If we take what is 5? Okay. If you have so any chance system degrees, okay, let us come to the next one. So Okay, just a moment. Just a moment. Just a moment. Okay. Spoilers. Sorry. What is the idea? The idea is, okay, the naturality property of the chain class says that the pullback of the chain class is the chain class of pullback. Okay, the Whitney property says that the total chain class is a product. Okay, so we use that, and then the most important thing is to prove that all the first chain class coincides. Okay, if you have a chain class theory, the first thing that you must do is to prove the normalization. So all first chain coincides. Okay, and use all the axioms in the proof. Suppose that this phi is another chain class type theory, so satisfy Witten and normalization. So up to pullback to the flag manifold. So this coincides, but the map from the flag manifold to the base is injected. So coincides, everything coincides. Okay, that's the idea. Okay, we have three equivalent. Actually, we have more, but a chain class we have used a curvature clause that we prove that is closed form, and the cohomology is the Hahn cohomology with real or complex coefficients. So in principle, the chain class has complex and real coefficients. Okay, by using this flag bundle, we can produce this chain classes, which is the same approach used by algebraic geometers. Okay, and via also by abstraction theory. So this shows us that the chain class has coefficients on integer coefficients. So the manifold is x zeta. So the chain class is in the image of this. I choose A. It's a ring. Okay, real, complex. Choose your preference. Okay, so by how to construct via abstraction theory, I can we can do that via primary abstraction to give Q frames everywhere linearly independent. So it's the abstraction to have some Q frames. So we have to use the Stiefel manifold and its it is homotopy groups. So you have to triangulize it. So for the 0, 1, you can try to extend a vector bundle to the second one, the 2 frame, and so on. At some point, you are not allowed to extend this. Okay? So the obstruction class of this protruder gives us a class chain which satisfies all the axioms. Okay?
Maurício, just
Wait.
let me make a small comment to complement.
Okay.
Because I really like these things that you are telling us. But I would just like to mention that there is a fourth one approach, if you want, that is a topological one.
Yeah.
Topology that is through the complex Grassmannians, let's say. So from this viewpoint, in topology, any vector bundle is a pullback of a universal one.
That
Is a tautological over the infinite dimensional Grassmannians.
yeah.
Then you can also show that they are the same, the same technique.
And by using the cohomology.
Of the Grassmannians,
Yeah.
Then that's why you may see that the cohomology of Grassmannians
Yeah.
is a
Universal way to construct it. Okay, thank you.
I don't know if that's actually the story or the truth behind it, but my way to understand this is that in some other instances, like complex geometry or algebraic geometry, you don't have this universal space, and then you kind of find the theory in another ways. No? And at the end of the day, you have the classes filling the axioms, so you are done.
I think it has. You just to change real for complex things.
Yeah.
The infinite P infinite, the infinite projective space. So I think it's work, even in the real, in the complex case. So thank you. Actually, I tried to prepare this, but I have no time. So anyway, thank you. So we saw that the top chain class is the dual, is the Poincaré dual of the zeros vector bundles. Vector fields, sorry. Okay. So, in general, the R minus Q, where R is the rank of the vector bundle, plus 1, A, okay, is the cap. Is the obstruction, is the Poincaré dual of the cycle S1 S key S the general loci of sorry, here skew and here n minus q plus 1. Okay, so this is the Gauss-Bonnet, generalized Gauss-Bonnet theorem. Okay. So from algebraic geometry point of view, by using Chow ring via projectivization, we can also define here X is a smooth quasi-projective variety of oval C, but it's much more general, okay? Because everything here for me is smooth. Even better. For me, it's better over C, okay? Okay, so write this AX as a ring, Shaw ring with zeta coefficient. So we project Vice by take the product of the symmetric power of the dual. In this case, it's just the projectivization of the vector bundle, and we set zeta the first chain class of the universal line bundle. So by Le Reich, okay, we can compute, or Grothendieck projective bundle formula, we can compute the Shaw ring, which here is clear how this the Shaw ring in the smooth case coincide with the cohomology ring. So this is a model, okay, generated. It's a free model that exactly what I say, what I told you. Okay, and the free base is the power of this class, the first chance class of the universal. So we have this equality. So this coefficients, okay, via a flag manifold, this coefficient gives us actually are the Chern classes in this theory. Okay, the normalization is just to say that this is the dual, the Poincaré dual of this line bundle. So because the projectivization of L is isomorphic to X and so on, but this is much more general approach. Okay. We have the Giesing map, which via the Giesing map normalized by this push forward, which gives us 1 on each fiber, and algebraic geometry prefer seg classes instead Chern class. Okay, it's more computable for them. So this is just the inverse of the Chern class. Okay. So how to come back to the usual Chern class by we can use the class map, which sends algebraic Chern class to the topological one, which born already with integer coefficients. Okay. We have another way to construct the Chern class theory on Kähler manifold, okay, which coincides with everything. If the manifold is not Kähler manifold, it doesn't coincide. Okay, we must to use another concept of Chern class, such as Bott-Chern class, Deligne Chern class, more refined Chern class theory. Okay.
So this cycle class map. Sorry, I'm not familiarized at all with the Chowdhury, but this cycle class map is an isomorphism in some cases, or what is known in general? For instance, when the manifold is moved.
Yeah, it's an isomorphism. This A M is smooth. X.
M small.
Yeah. Thank you.
Compactness, no?
No, no, in general. So this, in this case, by using representative DD bar and by using DD bar lemma, we can prove the uniqueness, axioms, naturality, weakness, sum, normalization. So let me let me recall you what is the naturality. Naturality is this property. Whitney formula is this one. So the chain class of the sum is the product. Okay, and either for k fixed, we can compute. So this is we can use the flag manifold to prove this property. So the splitting property is we use also to prove some properties of chain class things. Okay, so in order to do some computation, almost everybody do that. Okay. Okay. In the Kelly case, we have the so-called Atiyah class. So take a holomorphic. Now this kind of chain class theory, we have this chain class theory has analytic flavor. Okay. So E is a holomorphic bundle with we can take a chain connection. So and its curvature is going to be type 1, 1. Okay. So the Atiyah class it's element here, and by taking traces of this, for instance, by taking this and this. So we get a new one in the age KKX. Okay, and by DD bar lemma, metric chains, only representative DD bar forms. So in the homology, it's the same thing. Okay. Because in the Kelly case, the high double homology class agree. Okay, so we can define this by another way, which is actually the same way. The Atiyah motivation was to try to found an abstraction to get holomorphic connections. Okay, so we can define this, the Atiyah class of holomorphic bundle via the first jet exact sequence, which I will show you in just a moment. Just a moment, I will show you. So this is the trace of these gives us. This is already the trace. Sorry, this is coincides with Chanvey topological and everything coincides. So the first chain Atiyah class, okay, coincide on Keller case, okay, and satisfies all axioms. So coincides with all theory. So here, let me use a more analytical or complex point of view, complex geometry point of view. This is the shift of holomorphic functions, the shift of holomorphic one forms, and this is the endomorphism, the vector bundle of shifts, locally free shifts of everything here is a vector bundle, so this is locally free. So by using the dual homology, we can identify this H1. You can, in more general, if E is not locally free, this H1 is X1. Okay, so we have this identification. So this, if we have this holomorphic first jet sequence, the existence of holomorphic connection is the same. It's same to set that this sequence is split. Okay, so this exact sequence represents an extinction. Okay, this one is an extinction of this by this. So, in our case, this coincides with this H1, and which is the extension class. You can take a holomorphic cover, and by using the transactions of the vector bundle, the check representative is this one. So the Atiyah class is 0 if and only if E admits a holomorphic connection. Okay, so this is so strong, right? Not only all Chan class vanishes, okay, because all Chan class depends on the Atiyah class. Okay. So we have this theorem by Atiyah, which says as this Chan class coincide, the Atiyah class, Chan class coincides with everything. The sketch of the idea is by using the polynomial, which commutes with wedge composition. Metric change doesn't change. Metric change doesn't change the DD bar exact DD bar classes. So everything coincides. This is. Do you wanna let me give you the flavor of every single type of theory via Chan value? We had to use differential geometry. Abstraction is just a topology, Grothendieck algebraic geometry, and Atiyah complex geometry, analytic geometry. Okay, so you use in this case a connection in Chan value. In the abstraction theory, we try to trivialize on the escalator. I mean, by taking triangulation, it doesn't depend on every single choices. And here, Grothendieck has defined by using the projectivization of the vector bundle, the flags approach, and actually it's an axiomatic definition, and after they prove that this is the only class which satisfies all the axioms. Okay, and in the complex geometry, use the holomorphic structure of the vector bundle. Okay, so this cohomology lives here. The cohomology it's in the integer. This is the showering space, and here this class lives on the class of type KK type. The mechanism to prove the well-defined in order to descend to cohomology, use the chain class is via it's that proof that we gives we gave a proof by the closeness, and here we use the primary obstruction of the Stiefel manifold, okay, associated to the frames. This is a manifold of frames, okay, and here is split principle, and here in analytic case, a tier case is an obstruction to holomorphic connections. So the outcome is the Han, in this case, is an integer. This has an algebraic thing, and here on the Keller case, in particular on the algebraic case, okay, coincides. Okay. So the idea of a uniqueness we already saw. So Bott formula. What is the Bott formula? Okay, this is the main goal. This is my main goal in this mini course. So take a vector field and a complex vector bundle, differential vector field or holomorphic vector field. It depends. It's up to your taste, okay? And we define an action of V on E. What is an action? It's a differential operator on C in infinite sections, such that satisfy the Leibniz property. If you prefer, this is just partial connection with respect to the one-dimensional foliation induced by this vector field. Okay. So in the holomorphic case, in the holomorphic case, the action is holomorphic. We say that it's holomorphic with if this A commutes with the D bar operator.
It's the same as a lifting of the vector field to E?
No, I don't know. Maybe that is a way to do that, but in principle, no. I'm just take derivative along the leaves of the foliation. Just this. It's a flat connection. It's a flat connection associated to the one-dimensional. Okay. One-dimensional. I will give you. This is the definition of equivariant vector bundle. Okay. Our main prototype is the tangent bundle. So the action explicitly, in this case, is by taking the Lie bracket. Okay, Lie bracket satisfies this Leibniz conditions and so on. So theta is our main object from now on. Okay. Let me introduce a mixing between chain classes and in order to introduce equivariant theory of a localization, let phi or phi, let phi symmetric polynomial whose the degree is the rank of the vector bundle. Okay, this is just linear algebra. Okay, so take an endomorphism with eigenvalues. Okay, and define phi a by evaluating in these eigenvalues. So what we will do is it's mixing everything by using the root chance of the vector bundle plus the some weights which come from of the action. Okay, so formally this is going to be characteristic class multiplied by certain coefficients, okay, which generalize chain classes in general. Okay, we will see. Okay, so let's take the formal chain roots. So this exists by flag and split principle. And then phi is defined just by substituting this one formally by using Lehe-Hirsch theorem, the injectivity of Lehe-Hirsch theory. So let us assume that this has constant type. I mean, what I mean by constant type is eigenvalues locally constant on each component of what is X? Sorry. X is the manifold. Yeah. So sorry. Okay. So we can decompose this vector bundle canonically as a direct sum of generalized eigen subbundles. Okay, and we can do that by this assumption. Okay. And the next step is let X, the formal chain roots, and we group it there with, we put everything together with the eigenvalues. Okay? And we define the phi A as this formal class, which is well defined by symmetry of the blocks of the along the blocks of equal eigenvalues. Okay, just by sanity, let us check phi 0 e by taking lambda 1 and lambda so on equal to 0, we recove the total chain class. Okay? For instance, the determinant of 0e, I mean 0e, when we forget every eigenvalues. So the determinant is the top chain class. Okay. Once again, take a vector field and the action. This action here. This action here. Okay. By taking the bracket, what happened? The bracket is not it's a derivation, right? So, but if we restrict to the zeros locals of the vector field, okay, this vanish, so this becomes a tensor, okay? Okay. So now we restrict, okay, to n, and we have endomorphism. In this endomorphism, we can apply that linear algebra phi eigenvalues by splitting everything, okay? If your vector bundle is splitting, okay? So, if E is equal to the tangent bundle, the bracket action has a, has a kernel, which is the tangent bundle along N, okay? It's the tangent bundle of A, and thus this map restricts to the normal bundle, okay? And here we will define the degeneracy condition, but not the degeneracy condition, which is the determinant of the generalized, the determinant of the Jacobian. This is a generalization of the Jacobian of the vector field with isolated singularity, okay? So what I mean by what bot means by the degeneracy, this map is actually is an automorphism. So the determinant is different from 0, okay? And this means that we have an exact sequence, okay? So the kernel coincides precisely with the tangent, the tangent of the bundle of the singular set, of a connected component of the singular set. Okay. So this is the bot formula in this case for vector field with singularities of any dimension but not degenerated. Okay? So what is just by applying phi in A, okay, by considering the eigenvalues and the chain roots, and put everything together and then make the computation. So divided by this determinant, which is well defined.
Could you please repeat what theta is? Is theta? The theta. What is it?
Theta.
Yeah.
Theta is this map here. Which is the restriction, which is the restriction.
Like the right action, let's say.
Yeah, it's the restriction of the action on the,
Action.
which becomes a morphism. Okay. So this is the well-known Bott formula, which is the
definition of the left-hand side.
excuse me?
The definition of the left-hand side would be mine. How do you define?
This is just a definition.
Oh,
Excuse
this
me.
is a definition of residue.
No, excuse me. That is a residue. Yeah. This is the theorem. Sorry. Yeah. The integration of phi of Tx. Thank you. This is the sum of n contained in the singular set of V, and this and this one brought proof that we can compute this. Okay? I forgot, sorry, thank you. In particular, if the singular set is just a point, is isolated, and the eigen with eigenvalues, okay, and this is just this number. Okay, if you take phi equal the determinant, this coincides. Sorry, this m. Okay. If you take phi, quanto tempo tem? 40 minutos, pode crer. You take this, so the residue of Cn of this point at this point. This is the determinant, okay. This is the determinant of the Jacobian of the vector field. So this is actually lambda 1, lambda q over lambda 1, lambda q, which is equal to 1. So in this case, this is just the number of a singularity of the vector field. Okay?
In the case phi is a determinant.
Yeah. Okay. Why torus action implies? So now I'm gonna try to bridge bot theory to equivariant theory. Okay. Everything begins with bot. Okay. So assume that we have a T and a torus. Torus is actually act smoothly or holomorphically on a smooth manifold or variety or complex manifold or real manifold, and take this is MT is the set, M is the manifold. Sorry, MT is the set of the fixed point. Take a connected component. So, okay, for a generic element here, we can produce the fundamental vector field associated this guy here, which is by taking the exponential of this, the derivative of the exponential of this guy. Okay. So the claim is along n, okay, the kernel of the linearization is equal to n. So if the kernel of the linearization x of xv is equal to n, then satisfies the first condition of the non-degeneracy condition of the bot. Okay, if you work on algebraic geometry, and for me is not singular. Okay, it's always a definition of point. Okay, it's smooth. It could be singular one, right? But here it's not. So this is isomorphism, This is exactly the bots, the degeneracy condition along the connection. So how to prove that? Firstly, we have to prove the smoothness of the connected component. So in order to prove that, we use the so-called slide theorem, Palais or Lunas. In the complex case, that is avatar of this theorem, Lunas et al. Slide theorem. Okay, so locally, in order to prove this n is smooth, we have to prove locally, okay? Because smoothness is a local condition. So this theorem says that there is a neighborhood such that, and on a product such that we have this model, okay? So in this model, the locals, the fixed locals, is this, and the noble bundle identifies with the trivial vector bundle here. So if you have a torus action, okay, you must to try to find a vector bundle who vanish exactly on the fixed point. We already know if this vector bundle, this vector field vanishes there, so it's not degenerate. So what we have to prove that is that a vector field with vanish exactly on the fixed point. The answer comes from a very simple linear algebra assumption. Because the bad set of the elements of the Lie algebra, it's a linear space. So the complement is dense. So choose one vector field, and the bot localization implies this equivariant formula. Okay, so that's the idea. Choice generic vector field such that this is the character, okay? Character of this vector field, such that the character is not zero. So this is the same thing that. This is important because the action decompose induce a representation of a V, okay, where V is the tangent bundle act along the singular set. So we take a vector field away from these walls, okay, away from these linear spaces. So this vector field doesn't vanish away from the fixed point. Okay. So the idea is use the Palais-Slide theorem and take this vector fields, which the infinitesimal vector field, which comes from an element on the complement of this this problematic set. Okay. So by using now let us recall equivariant cohomology via Borel for this actually continuous smoothly. We have ET, a free contractible T space, which is the universal principal T bundle. So we take in your talk you're talking about this thing, okay? So the cohomology of this with Q coefficient, but it can be Z, okay, zeta, okay, such that this element has degree 2. So by Borel construction and homotopy coefficient, this is the space which remembers the manifold together with the T action. Okay, so by definition, the equivariant cohomology is the cohomology of MT of this space. Okay, which is, if you obviously if you take a point as a manifold, this is just this one. We recall this one. Okay, in the equivariant setup, we have this by definition this one, which is graded. This is just the symmetric power of the dual of the Lie algebra, and we use the cohomology of this complex. The cohomology of this complex is this differential with put together the Hahn differential and the contribution of the action here. Okay, this dt squared is equal to 0, so we have a complex, and in particular a cohomology which coincide the Borel cohomology things. So this is the Attia-Botti, Berlini, Venn theorem, so-called ABB-V theorem. Okay, by restrict here, so take an element in this cohomology here. Okay, this guy here, remember, AT is going to be by taking the determinant, okay, the determinant of lambda 1, the roots of the normal bundle, blah, 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 is the same thing, okay? So this is the formula, okay, for the equivariant thing. In the isolated case, this is just the weights. So this is huge. This is a generalization of a Bott formula. So sorry.
You wrote in the equivariant cohomology of a point localized. Do you mean n localized?
Yeah, localized.
But the point is n, or is really point? Is it typo? That's typo.
No, it's wrong. Localized here. Localized in the, sorry, localized in the here, not here.
It's typo.
Yeah, it's type. It's a misprint. Okay, thanks.
And now here, isn't it R? Isn't it a number?
Yeah, it's a number.
Yeah.
It's a number. Yeah. This is just the integration. Because if you take alpha it's, has differential forms times differential forms, only functions. So you integrate this essa coisa horrorosa, and just the highest thing contribute. Okay, so it's a number. Okay. here writing everything, this is just the composition of the fixed point. We now, from now on, we consider the equivariant cohomology, Cartan-Borel model, okay? Cartan, it's an infinitesimal model of the Borel model. We take if we take the inclusion and the normal bundle of F, which is smooth, okay? So it makes sense to say normal bundle, okay? The equivariant Euler class is an element here, okay, which is a product, which is a product with the t weights and on the normal directions corrected by certain shared classes, okay? So, but no degeneracy for a generic vector field implies no zeros weights here, hence this becomes invertible and localized and after localizing by non-zero characters. Okay, so more or less this is the definition of an integral in this cohomology. So we can prove that for each fixed point in localized equivariant, we have this pullback of the push forward of an element of the cohomology, equivariant cohomology of the fixed point satisfy this condition. So it's invertible, right? That's why we wrote down like this, because we allow to do that. So, okay. Let me give some explanation. This is the equivariant version of a Giese math. It's just a push forward in this context. The equivariant tone class of yields the equality, and since this has no zero weight by Bott degeneracy condition, this is invertible after localization. Okay? So this is the formula. Okay? We can arrive in this localization identity by using everything that I told you. Okay? The idea is just apply the pullback to the pullback to the fixed point, and after to push forward, and we use this this identity. Okay, so it's invertible. So and we sum over all components to construct alpha on reconstruct alpha on the whole space. So sorry, this is not a misprint. This is exactly this is a number. Okay, this is a number in the cohomology, equivariant cohomology. Is
without the integral, it's
yeah. By take the equivariant integral. This, sorry, this integration here. Okay. Yeah. All right. So this is the formula on an isolated point. This is key is just the t weights on the tangent bundle. On the normal directions. Okay. So what we need is the degeneracy says that we can linearize on the normal bundle which has no weights. Therefore, this is invertible by using tone and Giese identity. This is the sketch of the proof. So we have this general formula, which is a particular case of Bott formula. Okay? Okay, this is I'm repeating this, I don't know. Okay. What is a localization theory? Okay. What we can do about a general theory of localization. If the vector field has no singularities, that Chern class is equal to 0, right? So outside the singular set, everything is 0. So we need some vanish theorem, Bott, so-called Bott type vanish theorems. Okay? This is the first thing. So let me recall some duality. If let X oriented manifold of real dimensional with no border, okay? You can do with border, but I'm avoiding it. So let S a closed subset and take the complement, and we can define the relative cohomology by take the inverse limit every neighborhood which contains. This is the relative cohomology. So, okay, this is this N is open with shearing to S, and in the complements increase to U. Okay, which is the complement. By excision, for M is small, there is a canonical isomorphism between this relative cohomology and this one. Okay? And we take the colimit, which is stabilized by colimit. So therefore, we have this isomorphism. Okay. What is the duality that we will use is the Alexander duality with support plus Poincaré duality. Okay. So from the previous slide, we have seen that this is an isomorphism. So local Poincaré by cap with the Borel-Moore fundamental class of X, because I'm not assuming this is a compact one. Okay. So we must use the Borel-Moore cohomology here. The Alexander map is the following composition. Is the composition with this isomorphism. Okay. So what we are using is take a S, take a complement, take the relative cohomology. So this is isomorphism, the homology of the S, of S. This is the core of the localization. Okay? Now, by taking a Poincare dual, no compactness is needed because, as I said, we are using Borel-Moore cohomology. Okay, so localization identity in general is going to be this one. Okay, let me explain better. Okay, take a vector bundle, okay, with a connection, and I don't know if I want to, okay. With a connection, my course, the title of my course had a foliation, right? I just said one-dimensional foliation, so it's complicated enough to study one-dimensional foliation, flows and vector fields, okay? But in general, we have theories of residues, bound residues, Camacho side residues, Lehmann-Sua residues, and so on, okay? And then we can also construct characteristic class for singular space, such as Shan-Mathexon, matter, okay, and so on. So what we take is a subvector bundle, okay, here, and use the so-called flat connection in order to have this Bott-Vanish theorem. Okay, so we have this Bott-Vanish theorem. Thinking about the vector field case. It has no singularity. All top Chern class is equal to 0. Top Chern class has degree n, which is bigger than the codimension of the foliation, which is n minus 1. Right? Okay. So the idea is since the lifting, this guy is 0 here. So we can lift to relative cohomology in order to have an element here, in principle, non-trivial element here in the relative cohomology. This is not more. Okay. What is a general theorem of localization by using, so let us, we applied the Alexander duality, and after we apply the Poincare dual is this side, the side is the localization. So this is just the cap with x, okay? So we're gonna have some residues along the component, the connected component of the singular set of something. Choose your class of cohomology. If for some reason outside the closed subset your cohomology vanishes, you have a residue, localization and residue theorem. Okay, it's not difficult to prove the existence of localization. What is difficult to do is to prove what is the residue. Okay, this is just two box to apply the theory. I'm not saying this is easy to apply. This is the way that you can approach. Okay. But in some sense, actually, that is a machinery given by lemma is sua, where when they were able to say it, if you know the connections, the residue can be computed like this. CS is the secondary chain class in the last lecture that I did. Okay, take a small tube with a boundary which contains U, which is a strong deformation retracts, which means this has the same cohomology of S, the singular set. Okay, pick a connection on the complement, okay, such that this is 0. We have, in this stage, we have the vanish type bot theorem, and then we take another connection on the neighborhood of S. Okay? So this is the residue in general. If you are able to prove this vanish and choose the appropriate connections. So this is a lemma sua theorem approach. What is the big picture? A big in frame, the big picture. Okay, this is a misprint. Okay. The big picture, let us try to put everything together, algebraic geometry, and in a categorical way. Okay? Choose your geometry, for instance, schemes of stacks, complex analytic space, smooth manifold, or Whitney stratified spaces. Okay. So we have to use some morphism, embedded morphism, and take the complement, okay, and denote by J the complement. We need to consider proper maps to localize, okay, and we have must to have a certain Cartesian pullback square, which is the pullback and the push forward, okay. I mean Giesing, tone things, okay, composition. So attached to X, which belongs your geometry, take, for instance, a stable representable symmetric. We take a symmetric monomial infinite category denoted by Cx with 6 operations. Okay? Think about D modules. Okay? More or less the same philosophy. Okay? And we must have some compatibility. This is a typo, sorry, between the adjunctions and these operators, and some base change, such as Beck-Chevalier in Cartesian square in this category. Okay. We must have some projection formula and the QNet for this tensor product in this category, and this hum here it's important as well, and the whole localization is this triangle. This is you take more or less, you take the pullback also, and after the push forward, and we arrive in the identity of this symmetrically monoidal C-infinite category, and take B. Take B is take the Poincaré duality. No, sorry, this is the Alexander duality. Okay.
Is it a typo there in the bottom?
Sorry, where?
The bottom left should be the...
This is a typo. Where?
Yeah, on the bottom left.
Here.
Bottom, down there.
Down there?
Down.
Down?
More down.
Okay.
Left.
No, it's right.
Because shouldn't this be the co-unit?
Yeah. No. It should be. Sorry. You're right. Thank you. This is. And this plus one is just the integration, the Poincaré duality. Okay? Okay, if you are able to work in a category where you have everything, these operators, compatibilities, base chains, some projection formula, and this is the categorical way to see the localization theory. Okay. For instance, we must have the unity in this category. We have to choose some coefficients. I mean, if you take think coefficients is a shift of is a local constant shift, for instance zeta, c, and so on. Okay, I will give you some examples. You must have a Grothendieck-Verdier duality, okay, in order to try to explicit the residuals, right? Which is the home, okay? This is the dualizing object here, but okay, for an orientable real D manifold, this is just the application of these on D. So given A and integer D, we take the homotopy of this map from this unity guy in AD. Okay, this is displays the role the home. Okay, and we define this cohomology. Okay, this. No, it's a shift of A. Yeah. So we have a subscheme, a subspace. So we define this type of Borel-Moore zeta just like this by pull back everything. Okay, pull back everything to zeta. If X oriented of degree D, that is this guy and the canonical cap pairing producing indexes and numbers. Okay? And, okay. Now, vanish, we need a vanish on the opposite set. If you have a vanish on the opposite set, take a class here, okay? In the cohomology, in this cohomology here. Assume that we have this vanish by taking this functor, okay? This is the hypothesis that triggers the localization, okay? This is important. So by applying this functor to the triangle, we have this is zero if only if there is a canonical factorization. Okay, this is so that is only, no, actually it's not unique. That is a lift here. So by adjunction, we can localize everything by this functor here. This is just after fixing a orientation of degree 3. Okay. This is not a theorem. Okay. This is just a procedure. É só procedimento. Just a procedure to put everything together. Okay? Maybe I should write down a survey, a note about this approach. I didn't see it in any place, so maybe it's new, maybe it's not. So in this setup, we have the vanish, and then we have that I'm called the universal localization. That is a class, which is localization, which is the residues, such that what we need is try to remember the vector field case. The residue depends on the local behavior of the vector field around, nearby the singular set. Okay. So we need some existence, maybe some naturality. So maybe some functorial property. I mean, the pullback of the residue is the residue of the pullback. Recently, myself and Tatsusua, we proved that this holds on certain condition in a complex case. Okay. This is important because we can reduce the residual competition on the more simple space and the smallest space. Okay. Okay, and so the global index theorem is this one. Okay. So if you have any rule, you have to take some near excisions. I'm just so how to compute in practice. Choose two. Let me see. Choose this. Quanto tempo tem? 5 minutos. 5 minutes? Okay. So choose this. So pick a lift, okay? Pick a C chapéu, okay, C hat. So, and use the connected morphism to get a joint to localization and after pair each component and sum everything, and we have this. So the mechanism, it's completely concentrated here. Okay? Now take the pullback after the push forward. Okay? Here is just the identification of S. It's the embedding of S in X. Okay? This is the Alexander duality, and this is the Poincaré duality. Okay? Oh, so I have no time. Let me show you some examples. Okay. Specialization, manifold. This is the derivative complex, the Han complex, Cartan. A constant algebra, and equivariant. It could be this one, or ST, the symmetric power. So this is the algebraic set in this whole thing. We need a vanish, and the outcome is ABBV. So quasi-projective, we can take the spectral category, G invariant. A in this case is the unity in the K theory algebra. So after invert certain characters class, we have finished. So we can recover the Thomason and Lefschetz Riemann-Roch theory. Okay, so in algebraic geometry, we take the complex of shifts as this Cx, and A is going to be this Qx with natural transforms to the Borel-Moore homology. So this come back to Shen, McPherson, Todd, and the formula for singular spaces. But in the motivic theory, we can take this object. This is the homology intersection theory. So this one. Okay, I have no time, but we can do the same thing for in order to prove Lefschetz fixed point via localization, and we recover all these theorems by using this approach. Okay, so the universal localization theorem, if you apply in the right way by choose the right objects, if you have all the operations, the functors, we recover everything here. Okay, and also here. The last thing that that is also which is very important for algebraic geometry, and in order to compute Gromov-Witten, Donaldson, Thomas invariant, which is important for physics. So that is also this generalization for stacks, for instance. Obrigado.